Have you ever wondered how our universe came to be? It's a question that has intrigued humans for centuries. The most widely accepted explanation is the Big Bang Theory. This theory suggests that our universe began from an extremely hot and dense state, often called a singularity. Imagine a point so small and dense that it contained all the matter and energy of the universe we see today. This singularity is where our story begins. In this singularity, the laws of physics as we know them did not apply. Space and time as we understand them did not exist. Then, approximately 13.8 billion years ago, something extraordinary happened. The singularity began to expand rapidly. This expansion marked the beginning of the universe and the start of space and time. The expansion of the universe wasn't an explosion of matter into existing space. Instead, it was the expansion of space itself. Imagine a balloon with dots drawn on it. As you inflate the balloon, the dots move further apart, just like galaxies in our expanding universe. In the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion called inflation. This rapid expansion smoothed out any initial irregularities, like wrinkles on our imaginary balloon, and set the stage for the large-scale structure of the universe we observe today. As the universe expanded, it cooled. This cooling allowed for the separation of fundamental forces. These forces, gravity, electromagnetism, and the strong and weak nuclear forces, govern how matter and energy interact. With the separation of fundamental forces, the universe was ready for the formation of matter. In the first microseconds after the Big Bang, tiny particles called quarks and gluons combined to form protons and neutrons. These are the building blocks of atoms. In a process called nucleosynthesis, protons and neutrons came together to form the nuclei of light elements, primarily hydrogen and helium, with trace amounts of lithium. This process occurred within the first few minutes of the universe's existence. For about 380,000 years, the universe remained a hot, dense soup of atomic nuclei and free electrons. Light couldn't travel freely during this time because it would constantly scatter off the free electrons. This era is often referred to as the Dark Ages of the universe. As the universe continued to expand and cool, a significant event occurred. Electrons combined with atomic nuclei to form neutral atoms in a process called recombination. This transition allowed light to travel freely for the first time. The light emitted during recombination has been traveling through the universe for billions of years and is detectable today as faint microwave radiation known as the cosmic microwave background or CMB. This radiation provides a snapshot of the universe as it was just 380,000 years after the Big Bang. Over hundreds of millions of years, gravity drew together massive clouds of hydrogen and helium gas. These clouds collapsed under their own gravity, igniting the first stars and forming galaxies. Within these stars, heavier elements were forged through nuclear fusion, enriching the universe with the building blocks of planets and life. The universe continues to expand and evolve to this day. We see evidence of this expansion in the redshift of light from distant galaxies, indicating they are moving away from us. The Big Bang Theory, supported by evidence like the CMB, the abundance of light elements, and the observed redshift of galaxies, offers the most comprehensive explanation for the origin and evolution of our universe. It reminds us that we are part of a vast and ever-unfolding cosmic story that began billions of years ago with a moment of unimaginable density and temperature.